I'll just make a relatively quick introduction here to Dr. Rahul Razdan, who's here visiting us on his way to some degree from his home in Ocala in Florida, on his way to, are you going to Hungary?
Yeah, eventually.
Eventually going to Hungary. So he's just been awarded the Fulbright Association John von Neumann Distinguished Award. So Rahul has a very rich background, ranging from industry to academia, ranging from semiconductor electronics to currently working on test and verification of terrestrial autonomous systems. And over the last several years, I had a chance to talk with him about this as his ideas have been evolving. And so thank you very much for coming by. And without further ado, I'll turn it over to you and look forward to hearing what you have to say.
All right.
So welcome to Baltimore.
Well, thank you. First time at Johns Hopkins. I think the only thing I've seen of Baltimore before is, as I was going through I-95 in Massachusetts. So
Join the crowd.
yeah, I know, there you are. All right. So let me just kind of get into the talk. Okay, it's not that way. I just want to give you a little bit of that background because it sort of informs my thinking. So I come kind of from the world of semiconductors. So I was a CPU designer for a long time at Digital Equipment Corporation, Alpha Microprocessors. And then after that, I went over to a company called Cadence Design Systems, where I ran their functional verification business. After that, I did a bunch of research and startups and things like that. And these days, what I work on for the last, I don't know, about decade, approaching a decade, is thinking about verification and validation of cyber physical systems, but I guess ground systems being the big thing that we focus on. Although a lot of the work that I've done, for example, the airborne side, L3Harris has taken some of it and taken it in that direction. And I think it's general enough that it's applicable in other places. If you're interested in my work, I think the slides I'll send over to Jim and he can send it around. The academic work is in the usual places, IEEE, SAE. I did a bunch of work with, especially SAE, around sort of looking at the space in a, I guess, more holistic fashion and kind of figuring out what the difficult parts of this are, because as you know, especially if you're talking about ground, you're getting into legal liability issues and how do you define safety in the context of pedestrians and other such things. So there's a series that with SAE that I talked about that, and then kind of industry rags. And then if you don't want to really read all that stuff, I have a Forbes column where I try to be humorous. And how humorous I am, I think others can judge. All right. So this is just kind of an example of one of these SAE judge articles that are focused on test and validation. All right, I'm going to kind of go back to the basics. It's always good to go back to the basics because that informs, how we think about things. And the funny part is, especially when we talk about AI, it's interesting how a lot of these 8 basics are violated, right? So, but anyway, the first basic thing is, there's this notion of verification and validation, where verification is, do I match the spec that I have? And validation is, do I have the right spec? Does it actually solve the problem, right? And so it's an important distinction to have because it starts getting into these arguments about ODDs and what are we actually trying to do in some of these systems. There's an intimate connection between safety and reliability. So, interestingly enough, just referring to one of the Forbes articles that I talked about, everybody thinks that this autonomy stuff is really new. And from a liability point of view, how will the law catch up? Except that there's this whole body of law that exists around autonomy. We just call it equestrian law. And it's existed. And in fact, horses are autonomous beings. And in fact, there's this whole notion in that body of law that, oh, if I cause the accident by directing the horse, that's my liability. But if you as a third party do something to spark the horse or to have it behave badly, it's your liability. And by the way, once in a while, a horse just goes crazy. There's the idea of no fault, right? It's just interesting to think through because there is actually thinking about all of this sort of stuff, and there's a whole body of law that was connected to it. And so getting back to when we think about autonomous systems and liability, these kinds of things, definitions become very important. And maybe one thought I want to leave with you is, especially from a legal point of view, liability point of view, expectation functions are very important. So, trains run over people, but if you get in front of a train, you have no expectation that the train will stop instantaneously. And so whenever you have AI systems, one of the key things is what expectation functions are you setting with third parties, right? Again, basics, design for experiment. When we test things, when we verify things, we have this very, very simple-minded idea of we employ a stimulus, we look for a response, and then we have some criteria for correctness as a result of this response. Now, there's all sorts of variations of this. If you're talking about formal methods, we're thinking about, kind of a symbolic methodology for stimulus and a symbolic methodology for the response function, and also a symbolic methodology for correctness, right? But fundamentally, there's this, you have to have those three pieces somewhere in your system. And maybe for AI, I'll specifically refer to the criteria for correctness, which is one of the little failings that we have, because we often use AI systems where we don't really understand the problem. So what ends up happening is we don't have a criteria for success or correctness, right? Another key idea is this idea of operational design domains, right? So one of the ways that people get to, whether it's liability or even what are you going to verify around, is you sort of say, well, I'm going to define an environment under which I will say I work, right? And that's typically referred to as the operational design domain. And, around this, as soon as you do that, of course, you get into two very important ideas, which is, okay, if I define this, a domain, whatever I do with the design for experiment work that I'm doing, what's my argument for completeness, right? How do I know I've covered this domain? Or sometimes when you can't do that fully, because most of these spaces are, enormously large from a state space point of view, what's my closure velocity? So, how does that closure velocity connect to safety properties that I care about, right? So these are, again, basics. I'm not telling you anything that isn't really new, but it needs to be said.
Can you quickly define closure velocity?
Yeah, so what ends up happening is, in a lot of systems, is you sort of define, since you can't really cover the whole space because it's so large, what you end up doing is you define the space you don't want to go into, which are bugs. We'll call them bugs. And then you sort of say, in the methodology I have for generating stimulus and executing and hunting for these bugs, am I seeing bugs every once a day, once a month, once a year? And so closure velocity has to do with what does that closure look like, right? What does that curve look like? Because typically what will happen is at some point you declare victory because you believe that the probability of the worst case events that you're finding is fairly low in the environment. So that's what I mean by closure velocity, right? And then the next topic.
There we go.
Okay. Another key idea is the idea of divide and conquer technique. So if you sort of say, well, I guess the worst case is I'm going to test everything physically because it's the most real. But then I sort of say, okay, I want to test it in all the ODDs that potentially it can be in all its variations. Well, that's very expensive and likely not scalable, right? So everybody kind of recognizes that. So there are techniques that we use, and in fact, there are two major techniques that we use in order to attack this problem. So one is, can you by design do functional decomposition? That is, can you set up a system where if I verify a subsystem, then I verify another subsystem. When I compose these two subsystems, I can declare something about their joint verification. So that's a very powerful and important idea. And if you can do that, that's a very powerful. Typically, to do something like that, you introduce design constraints onto yourself, right? And then the second one is abstraction. So I'm going to split the problem in such a way that certain aspects of the system, the reality of the system, we're going to ignore because we have some other way of verifying that. And by the way, in chip design, we do this all the time, in the sense that, at the very bottom of our tree, as it were, is a transistor, which is these days functioning based on quantum effects. But very quickly up this abstraction hierarchy, the people above don't even know anything about that, because we have abstracted that function in such a way that it's verified separately, and then the people above that abstraction can take advantage of that lower level verification. So these two are very powerful ideas that if you can employ them, and they are, of course, in the chip world, we do employ them, but in the cyber physical world, we don't today. That if you can do it, that's how you kind of start attacking this problem. Any questions so far? No.
Well, I guess you're going to come to it, but I mean, it begs the question of what is different about the domain we're working in that we don't do that? Yeah.
Good question, Jeff.
Yeah.
It's just,
And
all right. So it's important to understand, and by the way, this is just going back to the Forbes thing. I once wrote an article that pretty much had the following thought process. Which is it compared astrology with machine learning and AI. And I just kind of asked the question, the thought experiment was, what's really the difference? Maybe astrology is just AI done by humans, right? And, you just sort of do that thought experiment. Somebody sits there and says, it just turns out, when Jim is happy, it turns out the stars are this way. And by the way, there's a 70% probability of that. And, how is it really different? Now, I guess I wrote that article with there's a serious thought underneath that, of course, right? And then there's a whimsical thought, right? And so the serious thought that's underneath is, if you don't know the underlying space, the characteristics of the underlying thing you're trying to model or look at, it's very difficult to understand whether you're getting closer or farther away from some solution, right? And so I just leave, that's AI. Now, getting to the verification space, it's important to understand from a verification point of view what underlying systems exist. No, I'm going to just now split, too largely. By the way, you could just as well say this is continuous and digital, right? But I just want to say that physical systems and I'll call it decision systems, or okay. So physical systems, interestingly enough, are really nice to deal with. Why? Because they have really nice properties. They typically have properties of moneticity, right? Which is, if you go in a direction and you keep going in that direction, you generally have sort of a well-understood function, at least from a direction point of view, right? As an example, if I'm testing braking, right? If I don't have an expectation that if something works, if the brake works at 50 miles an hour, whatever picture you want to use, it won't work at 30 miles an hour, right? This is using this fundamental idea of moneticity, right? And it's continuous, right? These are physical systems; they're continuous in nature, and that's a really interesting and important property. So when you're verifying stuff, you can use those properties to your advantage. Now, of course, the bad property, as it were, is everything is hyper-connected. These are, partial differential equations usually, and they're connected. And then depending on the values you're talking about, I guess in the worst case, you have the butterfly effect, right? Something happens over here, and through some exponential connection points, they can affect this other thing over there. And so typically, you have to sort of be aware of that. And as I said, this is one of the places where typically we use design methods to break this or to control this butterfly effect, right? So there's a rich history of validation using these in these traditionally mechanical systems, certainly in the automotive space. And the traditional safety field has developed a kind of a deep idea of risk assessment with an understanding of these physical systems, right? So those are physical systems, okay? Then we have digital systems, of which AI is sort of, I'll talk more about, okay? Well, by the way, they're some bad properties. They're not monotonic nor continuous. Oops. Okay, so all those nice properties that I could potentially use that in a way you want to think about this as a massive space, how are you going to explore it? In the continuous systems, you get gradients that you can use to your advantage, right? And in the digital systems, you can't, unless
This is the point I was trying to make on Friday, the difference between collision avoidance system and security
Interesting.
in digital systems.
Okay.
Yeah, absolutely. Now, there are some good properties. I mean, there's bad properties, okay? You have the potential to unchain connections because you basically get into sort of more event-driven sort of systems than continuous systems, right? So, and this is done with a combination of design, ODD, and thresholds, right? And then let's see. Oh, you have a potential to use abstraction to scale up the process of validation, and then you also have control. One of the I should have said that in the physical systems. Things like controllability and observability are typically difficult unless you sort of design them in. Whereas in the digital space, you can put those in. So, and there's a rich history of validation in this space. It just happens to be in the traditional hardware design and software design systems, right? Okay. What's autonomy? Well, it's the devilish combination of these two things, right? And so, and that's one of the, so it has all the, the good stuff from the physical systems, but by the way, interestingly enough, we lose. It's very quite interesting that even though the underlying system is physical, and even though in a AI domain, as an example, if you do perception, that things can't disappear because they're real, right? So there's continuity there, but we don't. Traditionally, we haven't taken advantage of that, right? Or so far, we haven't taken it. So those are problem spaces. Let me see. Okay. So now let me get into kind of more specifically AI, because what I refer to as digital systems, software and even traditional hardware has those properties. So this is a sort of a chart that kind of tries to get across a couple of points. One is, and obviously it's automotive background, so I gave the examples in automotive. But when these decision systems, when we started, when we wanted to specify a function, we had to design hardware, right? So we had to actually build hardware. And then, this idea of a processor abstraction came along, and we sort of said, well, okay, if we want to iterate on function, we don't necessarily have to redesign the hardware. We're going to have this soft thing, which is interpreted. And that created the software paradigm. The only problem with that whole paradigm was you needed all these software engineers, right? And then, of course, I would say this NLP-based, not NLP, now this neural net-based methodology where you have AI training and AI inference. And essentially, one way to think about all of this is the reason that there's a lot of power and why AI is so interesting is because effectively, you're you have the ability to get software written on the fly based on data, right? And and these are the applications that exist, and probably the people in this room and the virtual room all know all about this, right? The only problem from a validation point of view, compared to where we are before with software, is it creates a lot of issues. AI does, and again, if you're interested in just reading lightly about this, I kind of compare AI to kind of in physics, quantum physics, right? You have our traditional ways of doing algorithmic development, all that stuff, kind of mapping into the Einsteinian view, and then you have quantum, which has got the pseudo-random factor to it, and AI and ML algorithms sort of have the same pseudo-random probabilistic feeling to it. So the important properties that, especially from a validation and verification point of view, that are an issue are the following. So first of all, in conventional software, you typically have some kind of theory, logical theory about how something is going to work, and then you code around that, right? And of course, with AI ML at the extreme, I guess ChatGPT being the extreme example, there is no theory. It's basically they just work. And by the way, the definition of work is pretty fuzzy, right? Mm-hmm. Conventional software, it's analyzable. I can read the code. I can look at it, right? So ML algorithms are not analyzable. So in fact, a lot of the things we've developed in software validation, like code coverage and inspections and things like that, are very hard to do, if not impossible, in this space. There's causality versus correlation. And by the way, this difference becomes very important. I can give you a really pretty real example of this. Years ago, when I was at DEC, semiconductor fabs build these very complex models for the SPICE models that model the actual transistors. And at some point, somebody had the really bright idea and said, oh, these models are so hard to build because you have to get the underlying physics right and all that sort of stuff. Why don't we just take the data from the fab and piecewise linear build a model? Okay. And we did that. It sounded like a good idea. But then we started running into all sorts of interesting issues, right? So the first interesting issue you ran into was, the thing that this model uses on top is SPICE, which is basically a partial differential solver, and an optimizer sitting on top of a non-continuous function. That's not a good picture, right? So we started getting all these convergence issues, right? But then, more interestingly, the second thing that happened was, we're getting to about 80%, 90% pretty easily, but the last 5% is hard. And the physicists actually know what the effect is. But how do we actually get the model to do it? So you get that issue. Right? And then you kind of get this philosophical issue. We're trying to model the state of the transistor today. How far back is the data that we took from the fab still valid? Right? So you get into all sort of, and I was just trying, this is just to show kind of where some of this stuff going. By the way, how we ended with that was we said, okay, we still need physics-based models, which have the properties of continuity and so on, but the fudge factors will use the data, right? And that's, to my knowledge, still what's kind of done, right? Deterministic versus non-deterministic. This is an important one, and this is getting to my example about astrology versus whatever else, right? With conventional software, we, generally because we have the code in front of us, we can figure out computational complexity. In a lot of these things underneath, with AI ML, we don't know the computational complexity because we don't know what the underlying problem is we're trying to solve, right? Again, all of these turn out to be issues. So, okay. So this is just, this may be obvious to everybody, but this why AI is important. So that, the chart I gave before about hardware, software, AI, what I was trying to imply there is wherever software went, because software was this fundamental horizontal tool that we used everywhere. AI is very similar, right? And this is a chart that's trying to show at least my lifetime in the semiconductor and electronics industry. When we started, the blue is the use of electronics in generally in the G&A function in American industry or industry in general, I should say. So companies like IBM, DEC, Wang, so they ramped up very quickly. And then interestingly enough, today, if you look at IBM, it's still their same business, right? It's kind of flattened out, right? So the focus was kind of mainframes and then minis and kind of going after. The next kind of interesting wave was edge computing, which is laptops and cell phones and internet. And the fundamental thing that was happening here is from a business point of view, you can get to your customer directly. And so all the other stuff in between, were the needed pieces for that. And of course, the winners in that second wave and continued winners in that second wave are the people that participate in that ecosystem, the people that make the devices, Apple and the old traditional laptop makers. You have the people that did the internet, you have the people that provide the marketing sales functions, Facebook, Google, and so on, right? And this is still going. I mean, I don't mean to imply we're probably 50, 60% of the way through there because virtualization really hasn't made its way through the economy yet. But the next interesting wave is, again, kind of the picture of, electronics going to the edge. You have sensor systems, and then the sensor systems are highly mated with AI because the data generated from the sensors connects with the AI in order to perform and generally create intelligence. And one aspect of that is autonomy, but there are other aspects, intelligent infrastructure and all these kinds of things. And this wave is really just starting, right? This is something, this is really a chart, kind of a megatrend chart, where it's trying to show where, kind of, I guess, where the sweet spots are and where the challenges are. I mean, just kind of interesting, if you were to ask me today, where is the biggest penetration of autonomy in the world, in the marketplace today, is easily in warehouses. That's where autonomous systems are the most prevalent. And then you get into sort of, systems that are fixed form, like industrial situations and so on. And it's kind of gradually moving out from that sort of base. Okay, so we got this AI models, and this is a simplification. There's different kinds of AI models and all that, but I wanted to get this idea across, which is what do we know about them, right? So what's the right model and why? Interestingly enough, this is really pretty much empirical today, right? Yeah, there's some theory, you want to have transformers because of this high level effect, and you want to have feedback systems in these models, right? But largely, the way we decide whether some model is good or not is we say, hey, we ran it on this, and it seems to work, which somehow is a little not satisfying. Okay. Will a model converge? As far as I know, there's no theory to this. There's a team up at Harvard that works on a lot of this sort of stuff, the theoretical side. I just want to give this example, the difference when you employ the methods, the difference between I'm going to employ it for addition, vision, NLP, and astrology, they all kind of look the same. We sort of do a data analysis. We look at convergence properties, and then we declare victory or not. Now, this list of things is kind of interesting because imagine in your mind the thought experiment of training a model to do, multi-bit addition. We know how to do addition. We know the properties of addition, right? And and what's interesting is addition is a linear algorithm. for the lack of a better word. But we kind of, when we employ AI on it, we actually turn it into an exponential algorithm because we enumerate all the databases and then we try to get the model to learn. And at the end of the day, after all of that, it's very hard to tell whether it's working. It seems like it's working, but we never know if there's like a nook and cranny somewhere where it won't work, right? And we don't really know the kind of the important properties of addition that we all understand. Like if you add two things that are positive integers, the third thing should be at least as big. Are those properties maintained? We don't know, right? So, and then NLP and vision, these are successes. And again, I talked about astrology already. It's a lot of these systems, and I don't have time to get into the details of this, they're very brittle in nature. You know, there's many examples of, you know, you introduce the right sort of white noise and you can confuse the systems, right? And you know, what's robustness to noise and how does this learn and what's noise anyway, right? So these are all kind of interesting questions. All right, so the bottom line of this is, how do we know it works? Okay, you know, it's just kind of a thing. So I'm going to give a little example from electronics, and maybe as I was, you know, a personal sort of story might be connected. So electronics. Design, hardware, verification. I mean, I did that for, I don't know, 35, 40 years, right? So know it quite well. And when I started looking at the AV space specifically, it appeared to me that a lot of the tools that we use in semiconductors are not being used in this space. And so I obviously said, hey, can we use them, right? You know, and kind of went down that path. I want to get across two ideas here that are really important in electronics and semiconductor design and verification. So the first one is there's this mapping from physical to virtual. You know, most chip designs, the person does not see the actual chip years later. It's all virtually done, right? And so how does this work? Well, what happens is that there is a kind of a lots and lots of interesting abstractions that are used as intermediate points for the design. And the first most important one is the mapping from the physical to the virtual of the actual devices. Maybe more importantly, when we do design in semiconductors, we have this very important idea of function and interconnect and isolation. Those three things give you that composability property that I was referring to before, right? So you know, the fab goes off and it does the, you know, quantum effects and advanced materials processing, but at the end of the day, all of that comes down to a SPICE model that the next level up uses, and the fab provides that SPICE model. Right now, is it perfect? You know, the natural physical world is hyper-connected, right? You know, you have capacitance and coupling, and you have inductive. But all of this exists, right? But it's just how we deal with it is through a series of methods that lead to something interesting. And then above this, and you know, is we use a lot of abstraction. So even the first level of abstraction, which is a SPICE model, if you took the whatever billions, I don't know what it is these days, of transistors and try to analyze anything at that level, it just wouldn't work. So we have to, in order to get the closure velocity, to get the scaling that we need, we use lots and lots of abstractions. And this is just, you know, these days, you know, we start with transistors, we used to have space level models. We have gate level models, we have RTL, obviously above that, we have IP blocks these days, we have chiplets we're going to go into as models. So these two things have allowed us to do this. So this is the semiconductor ecosystem. It's probably, I don't know, a couple of $1 trillion, completely enabled by these abstractions. If these abstractions did not exist, then the liability structures between the major pieces here are completely dependent on that. TSMC would not exist without these abstractions, right? So, so I guess that's one way of saying it is that it seems like there's a vector here that's interesting. Okay, now we get into a kind of a traditional autonomy stack. So, you know, I guess it's fairly straightforward. You have some kind of sensing function. Typically that goes into some kind of, and this is obviously coming from automotive space, but you know, change the physics a little bit, and it's a play, and it changed the physics a little bit. You know, the sensors are slightly different. You know, but it can apply to other places as well. So you get sensors into perception. It's typically some kind of path planning. You can have location services, and then some kind of actuation, right? So, and I guess 2 points here, observations are, the left is very physical in nature, going back to my physical digital divide, right? And then the middle, certainly is very digital and decision-making driven. And then the right is, I guess, is the action. It's more control system oriented. So, so I think the question, like, you know, kind of given the background I just gave, I kind of sort of, I look at this and I sort of say, what are the interesting abstractions between these phrases that we can build, that we can do divide and conquer, right? That's an obvious sort of question to ask. Why, when I'm verifying the prediction or the localization, why am I not taking advantage of the fundamental physical properties of the underlying system, right? Rather than looking at the bits and bytes that are there. Would that be useful? You know, these are sort of the questions that sort of come to mind. Is there a design simplification that would allow me to do the composability that I'm looking for? So these are, you know, the high level things that from a point of view of research, you know, I'm interested in looking at. Okay. So what do people do today? So one of the things that I actually work with, I think Elsie Harris on this. So for system, where you have system level specification, like in defense and places like that, you have a better starting point, right? At least you have the system spec. And if you have AI components, you kind of think of them as software plus, right? In other words, it's a piece of software. Everything else, how you verified software, you try to reuse as much as possible, right? And then the fact that it's an underlying AI component, you try to deal with separately. And you know, no structure, training data is the program. How do you actually, you know, verify the training data, and how do you measure completeness? So one flow that people are starting to look at and use is that kind of idea. And often this has to do with things like, how do I take the training data and characterize it against the ODD that I'm trying to go after? Things like that, right? Okay. Now, unfortunately, besides the defense guys, where people tend to use AI is where they didn't know how to write the system spec, which means there's no system spec, which means, going back to the design for experiment that I just talked about, it's a fundamental part of the V&V process. Determining correctness is kind of difficult, right? So this sort of it's problematic, right? It's likely. And then the toolkit that exists out there, you know, obviously system spec when available, use it. Often the way you deal with this, you don't have no system spec, is you create an anti-spec. And then what's an anti-spec? The anti-spec is, I don't know how it's supposed to work, but I know what I'm not supposed to do. I'm not supposed to hit other things, right? And so you in my world, you would call those assertions. You assert things about the system, and then from a validation point of view, you try to create the scenarios and the situations that force this thing. You know, so collision systems. So one of the classic cases with these kind of adversarial AI systems is you basically have the model under test, and you have other actors, and this thing has an anti-collision system, so you try to create collisions, right? These kinds of things.
But I want to push back a
Yeah.
little bit because it's just not clear to me that, I mean, if you take some of the really big successes of AI, for
Mhm.
example, in protein folding, would you say that you don't have a system spec there?
I don't know protein folding well enough, to.
Actually, I don't either.
Where AI has seen success, I would make this following general statement.
Okay.
Where AI has seen success has been where it's been used in the as a performance aid versus the fundamental algorithm.
Hmm.
And just going back to my CPU design sort of background, all CPUs, especially scalar CPUs, have something called a branch predictor. You know, we should have called it, you know, LLM AI to get more money or something. You know? So what are branch predictors? You know, branch predictors are data-driven guesses at where the program will flow, so that you can use that for performance. But what all systems do is when that's wrong, you can unwind, but what you want it to be right most of the time. And if it's right most of the time, it's an enormous performance gain, right? So wherever it's used in this sort of performance context, it can have great value, and it does have great value. But the question is, and now let me go back to my mapping of quantum effects, right? If something is fundamentally probabilistic, and one of the things that you can do is you can sort of say, yeah, I'll use it in this performance context, but my actual gating function, it needs to be gated by something, right? Which is maybe a functional thing.
Mhm.
And you see this, by the way, increasingly in AVs. You know, what happened in the beginning was everything was AI systems, and there was a thin safety layer, right? And now, as we learn more and more, the safety layer is getting fatter and fatter, right? You know, and these things are almost, this is a philosophical thing. They become recommendation engines,
Huh.
right?
Yeah.
So that's a kind of a way of thinking about this. At least to my knowledge, where we've seen great success is in that kind of context, or where safety is not an issue. You know, recommendation for your next movie or whatever else, right? So I don't know if that's, so on the protein folding side, I just don't know,
I was just trying to think of, AI applications. I mean, image processing. I mean,
Yeah.
you have I guess that you have a fuzzy spec there, right?
Yeah.
Because you say, well, I'd like it to recognize cars,
Yeah.
but I don't really have a good way of testing that other than testing against every possible picture
Correct.
of a car. Yeah.
Yeah, well, it's not like that. If you have a validation headset, here's what you start thinking. It's like, I want it to recognize cars. Oh, by the way, I want to have it recognize cars that I rotate in any direction.
Yeah.
And I still recognize the car. Oh, by the way, if the car is obstructed for an instant because another truck is in front of it, I still want it to recognize the car because the car really exists, right? So you get into all those kinds of thinking processes and the fragility. So one of the things is, depending on the data set and what it's seen, these algorithms are kind of naturally very fragile. Small deviations can throw them off. And so what ends up happening is, again, a combination of this with, let's say some fundamental idea of continuity, inertial physical continuity in a broader system, sort of that becomes more successful. So you sort of say, well, I recognize a car, okay? Now in some other system, I know it's a car, and cars move in the following way. So when I don't see the car in the middle, I know the car is still there, right? So this kind of combination where the two things interplay in some interesting way seems to be more effective. Yeah.
Jim, I think one thing that you're suggesting is that there are some applications where implicitly you have the luxury of determining correctness at runtime, like discovering new materials. Yeah, if the AI system gives you something that doesn't make sense, you can discard it, of course. Unlike safety critical system, where you want to make sure you don't run into a wall,
Yeah,
you can't.
yeah. It's too late to say, oh, sorry.
Yeah, it didn't work out.
Although it sounds like the Tesla systems were doing that, like, oh, it's not, I think it's your job.
A work in progress. Unless the system's so bad it becomes annoying.
Yeah.
But if every now and then, so you're gonna test, to make sure that material has the properties that the system believes it does.
Yeah, I guess sort of what's kind of, it's sort of what part is broken, right? In
Yeah.
our, so is it really that we can't write the spec well enough? Is that really the root of the problem? So.
Well, I mean, I think there's two, I'm going back to the quantum physics thing, right? So I like that analogy.
I just know too much about quantum.
So the way I think of it is it's inherently probabilistic in nature, right? So I think it seems to me that if you can use its inherent properties to its advantage and know how to use it, because it has rules of operation, as it were, then it's perfectly fine, right? I mean, so as an example, if it's helping you with recommendations for your next movie, or it turns out with NLP and the way they've done it that it's reasonably predictive for grammar and things like that. And you can decide very quickly afterwards whether it's useful to you or not. It's obviously useful in those contexts. I think where you start getting into trouble is if it's inherently probabilistic in nature and you don't understand, it is not understood the nature of the divergences you can get, and you put them into safety critical systems, that's when you start getting into problems.
Too many inputs, not enough structure.
Yeah.
I mean, a calculator has a lot of potential inputs.
Yeah.
But there's structure, as you pointed out earlier.
Exactly.
You
Yes.
can take advantage of.
Yes.
It's that bad combination with the third safety critical.
Yes.
That trio is really a really bad combination.
Exactly. And so one of the things you start getting into the spec issue is, and this is one of my pet peeves in the AV space, is what is
Autonomous ventilators.
Yes.
Keep going.
Okay. So one of the things is the implicit definition of the spec today in autonomous vehicles is, in its broadest sense, is, oh, it's just like a human. Okay, and that, which obviously is not true, right? But nevertheless, that is the projection of expectation that's done. And that gets into lots of problematic things, right? You're much better off actually, sort of broadcasting expectation function that then not only can you test against, which is the important thing about the expectation function, but you can also let third parties know the limitations, right? Like a very simple example is when your Tesla is in auto drive mode and it's not, and you're a third party, do you have a right to know? I think eventually we'll say, yeah, I have a right to know, because by the way, another just kind of a little thought piece against another Forbes article. I saw this thing, this HBO series about this lady, Temple Grandin. For those of you that, by the way, great HBO thing. But it got me thinking. So, okay, it's about autism. Do autistic people drive? Was my question, right? Do they drive? And so it turns out there's a Society for Autism, American Society for Autism, and in fact they address this point for the kids that are autistic, and they have this chart, and the chart basically says, if your child is not good at social cues, you probably shouldn't let them drive. Okay. By the way, the obvious next question is the AV has no clue about emotional cues. So, but I think, I mean, like I said, a lot of these things end up being deeply thoughtful, philosophical in nature in terms of what is the driving task? Is it a social collaborative task? Probably to some degree.
Yeah.
It is, right?
Yeah, so John Leonard used to have a lot of these stories, right, about, driving in Boston traffic and
Yeah.
how the social cues were the only way that you actually managed to make
Absolutely.
that left turn into, yeah,
Absolutely, yeah.
Four-way stop signs.
yeah.
Well, and then you get into all sorts of, there's a,
Excuse me for a moment, I'm just realizing how close we are
yeah.
to an hour.
Oh,
Yeah,
I'm almost done, yeah.
almost done, so we should probably let you get done and then see if anyone online has any questions too, so.
Yeah, I'll go very quickly. So in order to attack this problem, what I noticed in the autonomous vehicle industry was we all had private stacks. So, Tesla has their thing, Google has their thing. So it was very difficult to make progress. So what we did was we built an open source stack that had an underlying system, and then we built verification and validation capability around it. So this is really about that stack. These are the people that are involved so far today, although others are joining. And it has all these properties. If you want to take a look at it, the materials are in there. Okay. Yeah, so there's simulators, test generators, things like that. But the idea of this is really, how do I accelerate the learning in this area? And how do I get to these divide and conquer sort of methods and other such things that, oops, I don't know how to go back. Well, it's all right. It's, oh, there you go. Okay. So the actual framework, is trying to kind of answer these sorts of questions. And then, but much more importantly, what should be the interfaces between them?
Mhm.
I personally believe where we'll end up, much like we've ended up in semiconductors, is these intermediate points become standards. And then, there's a huge amount of, the software machinery that helps you manage this sort of stuff. But we haven't discovered what these things, what the interface should be and what the viability of them. I mean, just to tease out one particular one, you might want to say, well, I want to verify the sensors separately from all this other stuff. Okay. Well, okay. To what degree should the sensors, what do you declare as the sensors saw something? And you can define that, right? Okay. Well, then you can test it separately. Then you can sort of say, well, okay, if things are seen to this level through the perception engines, what do they do with it? And then you start separating the problems out, right? Okay. By the way, within this system, we have lots of test cases. We've got, existing deployments of like people movers, autonomous people movers in Jacksonville. We've got various accidents that have occurred. This is all meant to be a research framework where somebody can just jump in and get a lot done. You just kind of go, again. Well, okay. I guess I'm done. Well, I was going to say is the important questions here, I've already alluded to a lot of them, is what are the right abstractions that we want to build above this fundamental layers in such a way we can reason about these things, and both from a design and validation point of view. It seems to me, starts addressing some of the issues of the underlying brittleness that exists in these systems. So like you might want to say, like I said, if you're in a physics-based system, which we live in a physics-based Newtonian system, things can't disappear. They have certain momentum. You can't accelerate. All these sorts of properties are properties that are inherent in our environment. It might be slightly different in air and in the marine space, but nevertheless, they exist. Seems like it's a good idea to define them. It seems like it's a good idea to imbue them in these kinds of systems, right? Mm-hmm. But what do they look like? How do we actually do this, right? Is sort of one thing. And then similarly, what are design parameters where we can get this separation of concerns, right? Can I actually, the sensors, perception engines, location services, can I think of them separately and some have some properties of composability that are interesting? That's another set of interesting things to look at. How do I think about this from a scaling point of view? Where we ended up in the semiconductor space was if you looked at, any of these kinds of chip projects, you've got basically server farms full of test generation and evaluation engines. So in that world, path tracing through search spaces is a very important thinking process. So what does that look like here? And again, I'm going to go back to the physics-based underlying physics. If you don't have the underlying physics and you're trying to verify this prediction engine, you very likely will go down pathways that are not possible in the physics, right? You start, oh, well, what if this thing suddenly in 2 nanoseconds does something? Well, it's not possible in the problem you're solving. You make the problem. So there's a sort of a whole level of sophistication that can be done, which right now, as far as I know, let's say in the AV space, there's 2 or 3 things that are happening which don't seem viable. So the first thing is people have a thought process of, I'm going to just prove this by putting it out there and I'll get 1,000 cars or 1,000,000 cars in the case of Tesla. Well, the search space is too big. And my analogy for that is that's the equivalent of me in my old days, shipping bad software to a million mainframes and then saying, well, let me get the crash dump and try to figure out what the hell happened so I can fix it. It doesn't seem like it'll scale, right? So that's one way people have decided to attack this problem. Another way people have decided to attack this problem is to virtualize to a certain degree, but then they have a fixation with accuracy or fidelity, right? You'll hear a lot of these kind of words. But the virtual thing has to be super accurate. The only problem with the super accurate is, of course, from a scaling point of view, the turn rate goes very much down, right? The more accurate it is, the slower the models are and so on, and therefore their usefulness is very limited. And how we solve this on the semi side is you basically use that on a very small part of the problem, but you use abstraction very powerfully above it, right? So what are the equivalent things there? Okay, I'm done. Sorry.
Tony, you have the ability maybe to see, are there any questions? If people have any questions, we should maybe take another 5 minutes here, and if there's any Q&A.
We have about 10 other people.
Yeah.
So I'd say if you have a question, assuming that you can hear me, just unmute and ask the question.
Yeah, there we go. Yeah.
Hey guys, I have a question here.
Talib.
Yep. All right. First of all, thank you for the presentation, Rahul. This was very informative. I'm also familiar with one of your the projects that you were involved with, the Polyverif simulation environment for simulating autonomous vehicles and their functions. My question is more related to the formal verification part. There's this problem in formal verification that's called state space explosion, like when you define
I'm familiar with it.
Exactly.
Yep.
When you define a system, you're using formulas that get complex and you get tons of states, and symbolic execution becomes a burden when you try to verify all the states. What role can AI play in reducing that space? To make formal verification faster, consume less resources, and just gets done the fastest possible. Yeah.
No, well, so maybe let me answer this in 2 ways. Just separating, and there's one idea is the idea of how do you make satisfiability engines better, faster, and things like that. And you can obviously use heuristics to do that. And whenever you say the word heuristic, it's always good to use something like AI for aiding that process. Now, the fundamental complexity won't change, right? But there was a book a long time ago of computer algorithms where whoever wrote that book was a physicist and said, while the order of magnitude doesn't change, 2x is a big deal. Right? So there's that thrust, which I'm sure there will be a fundamental progress in the underlying satisfiability solution methods, probably connected to the domain space of interest. But the other one that I think is interesting is, let me just tell you how formal verification ends up being used very powerfully in the semiconductor space. There are two ways it's used. One is when we go through these abstraction levels, and the abstraction levels are close to each other, as it were, the logical distance is small. Just to give you a real example, when we take a layout and then we compare it to a net list, we actually do an abstraction and do a graph isomorphism method. Or if we take two net lists that are very, like there's a small change and you want to make sure you haven't messed things up. Formal methods are used very powerfully in all those situations, right? So what the next question is, what are the abstractions in this space, and can we use them in a similar way there? The second thing is way we use them in semiconductors is we assert things and we try to prove those assertions. And if often these assertions can be proven through formal methods because there's sufficient locality in the logic that it can be locally proven. And so that is done quite a bit as well. So my suspicion is the formal methods are going to be useful in those ways in these domains as well. Did I answer your question?
Yep. Thank you so much. Yeah.
Anybody else? Anybody awake? It's a late afternoon, raining outside.
Yeah. Well, we did run over a bit here, but yeah, I think if we don't have any more questions, we'll just sort of thank everyone for joining us. We did record it, so we'll post it to the.
I'll send you the slides.
Okay, marvelous, and we'll get the slides, and so thank you very much for coming and joining us, and having us. We'll continue the conversation.
Absolutely.
Okay, thank you all for joining us. Bye.
These are the issues.